let's get started with chapter 10 then. Like I said, I'm going to skip the PowerPoints for this chapter because it's going to take too much time. I'm just going to I'll do a brief rundown of chapter 10. Title of chapter 10 is stoichiometry. Stoichiometry means quantity in relationships. And so if we look at methane combustion, so we combust methane. When we combust it, what does it react with? Oxygen. And what does it form?
Water.
Yeah. And then we just need to balance it. So methane is a gas. O2 is also a gas. CO2 is a gas. H2 is a liquid. This is a redox reaction. There is a driving force. We are going from stronger to weaker. It's hard to see, but here, the stronger oxidizer is O2. What's the weaker oxidizer on this side? It turns out it's not water, it's CO2. CO2 is the weaker oxidizer. Is CO2 a powerful oxidizer? No, not at all. No. Not really. In fact, CO2 is used to put out fires, not to fan the flames. So you wouldn't be blowing oxygen on top of fire because oxygen is a good oxidizer. And so this is going to be balanced out like this. That's balanced. Okay, so the first quantity relationship are the stoichiometric ratios. Stoichiometric ratios. The stoichiometric ratios is a 1 to 2 to 1 to 2 ratio. So I need 1 part of methane, 2 parts of oxygen. These are mole ratios, right, or molecule, mole or particle ratios. But we can also have mass ratios. And chemical equations are always going to be mole or particle ratio or molecule ratios. If we look at the mass ratio, then maybe you have it memorized. What's the average mass of a carbon? 12.1. Hydrogen is 101, so it's 404, so 1605. 16.05 grams is 1 mole of methane. What's the average mass of an oxygen? 1600, which means 2 of them is going to be 32, which means 4 of them will be 64. So it's going to be 64.00. So if I take 16.05 grams of methane, 64.00 grams of oxygen, then I have what's called a stoichiometric ratio. And so this is also a stoichiometric ratio, but in terms of mass. Stoichiometric means just the right amount. So this is mole ratio. How many grams of CO2 do I form? Well, carbon's 1201, oxygen is 16 times 2 is 32, it's 4401. 4401 grams of CO2. And how much water? Well, the water I've memorized, 1802, 1802 times 2 is 3604 grams of water. And so these would be the mass ratios here. The mass ratios are inconvenient. Do you want to memorize mass ratios?
No.
Do you want to have to derive the mass ratios? No, so we don't really do it. It's not used. It's not used. Because it's inconvenient. But it's handy because if we know the mass ratios, then we know the right amount. So for example, if we have 16 grams of methane, we better add 64 grams of oxygen. So we know the right amounts. The problem is this. Can you measure out moles easily? No, measuring out moles, we don't have a mole meter. A mole meter would just tell you, oh, this is how many moles. There's no mole meter. We have a mass meter, which is called a balance. We measure out volumes. That's not a problem. And so in stoichiometry, we're often concerned with this. And so So let's look at a stoichiometry map. At the heart of the stoichiometry map is a mole-to-mole conversion. And so we go moles of A to moles of B. And so A, we could just pick anything. So if I need 2 moles of CO2, how many moles of oxygen? Clark?
4.
4. And so this is just the mole ratio that we use to interconvert. Okay, if I want mass, then this is the way we'll do it. You know, because measuring out moles is difficult, we can measure mass. If we measure mass, then this is the way we do this here. The way we're going to do this is we're going to go from the mass of A to the moles of A. You know, we could go from the mass of A, let's say if I had 4401 grams of CO2, how many grams of methane do I need? I need 1605 grams of methane. We could use the mass ratio, but it's too inconvenient. So what we're going to do is we're going to go from mass of A to moles of A. So doing a gram to mole conversion. A gram to mole conversion, we're going to need the molar mass. Invert it here. And then we can do a mole to mole conversion, and then we'll do a mole to gram conversion. So we'll go to the mass of B. And so this is your standard basic stoichiometry problem. This is a basic stoichiometry. So let's do an example here. For every pound of CO2, I mean not CO2, CH4 combusted, methane combusted, for every pound of methane combusted, how many pounds of CO2 is generated? How many pounds of CO2 is generated? So those pounds, those are typical mass units that we use?
No.
No. And so what we're going to do is we're going to do the stoichiometry map here. So we'll rewrite the equation like this. And then we'll start off with 1 pound, 1 lb, 1 lb of CH4. And so we need to go from pounds to what? Grams. So we'll go grams of CH4. And then we go from grams of CH4 to moles of CH4. And this takes us to the stoichiometry equation and the stoichiometry math here. And then from moles of CH4, we're going to go all the way to moles of CO2. It's a 1-to-1 mole ratio. So 1 mole of CO2 forms for every mole of CH4 combusted. And then from moles of CO2, we're going to go to grams of CO2. And then from grams of CO2, we'll go to pounds of CO2. And so this is just the dimensional analysis. So we're going back to dimensional analysis here that we talked about earlier. And so our given here is 1 pound. And so we'll start off with that. 1 pound of CH4. Okay, then we got to get rid of pounds or pounds of CH4. In this case, we're just going to get rid of pounds. How many grams are there in 1 pound? It turns out there's 453.6 grams. Pounds. So pounds cancel. Gives me grams. And then we actually already calculated the molar mass. There's some 16.05 grams of methane for every mole of methane. Here. And then we know from the stoichiometric ratio, it's 1-to-1. And so 1 mole of CO2 forms for every 1 mole of methane burned. Okay, so where are we at now? Grams of methane cancel. moles, methane cancel, and that leaves us with moles of CO2. And then we know that there's 44.01 grams of CO2 for every mole of CO2. Moles of CO2 cancels, and then we're going to go back to pounds. And so for every 1 pound, there's 453.6 grams. 453.6 cancels here as well. That leaves us with pounds of CO2, grams cancel. And so let's go ahead and calculate that. It's going to be 450. Actually, I don't have to do that. It's just going to be 1 divided by 1605 times 4401. 2.7. How many sig figures am I allowed?
4.
Yeah, in this case I'm allowed 4 sig figs. Because we're going to take 1 as exact. And so let's write this up to 2.7420 pounds of CO2. And it's kind of weird because it seems like, you know, the masses aren't balanced. But masses are actually balanced, you know, because 1 pound of methane generates a lot more CO2 because CO2 is a lot heavier molecule. And methane is only 16 grams per mole, but CO2 is 44 grams per mole. And so even though it's a 1-to-1 mole ratio, CO2 is a lot heavier. And so we're going to get almost 3 pounds of CO2 for every 1 pound of methane combusted.
Couldn't you do that without the moles? Because we already know the mass of them, so couldn't you just divide them?
Yeah, except we don't want to write out an equation with mass ratios. If we write an equation with mass ratios, it's going to look like this. 16.05 grams of CH4. I mean, we could come up with a mass to mass ratio here, but first we got to figure out all the masses. We don't want to figure out all the masses. We just want to figure out the masses for the ones that we want.
Right, so like...
Yes, the answer is yes, you could do that. Go ahead and do that. There's no problem to do that. It's just after you do a bunch of these, you'll see it's going to take more time than just doing this. Mentally, it takes more time because it's just, you know, but there's no problem with doing it. In fact, if you want to do it that way, you're welcome to do it that way. But we got to come up with the mass ratios. And so this is the mass ratio you got to come up with: 4401 grams of CO2 for every 1605 grams of methane. But it's 1 step removed from this. Even though this might seem it takes more time, mentally this is better because it reinforces this, so you see it more times repeatedly. All right, that's your basic. This is 1 step advanced. You know, 1 step advanced, I give you pounds, right? Let's give you another step advanced. We'll do another step advanced. I just need, I would give this to you. In Chem 1A, I wouldn't give this. I'd expect you to be able to figure it out. The mass percentage of oxygen in the air. You know, I know about how much oxygen there is in air, right? But you know, how much oxygen is there in air? You see there's 20.95% oxygen. Do you see that? But there's a trick to this percentage, and that percentage is by mole, or is that percentage by mass? This is a percentage by mole. In Chem 1A, you should be able to convert a mole percentage into a mass percentage. But in Chem 4, I'm not going to make you do that. I just give it to you.
And so we need to figure out what the mass percentage is. Yeah, here. We'll just use this. We're going to use 23.1%. Oxygen is 23.1% by mass in dry air. Yahoo Answers is very inconsistent, but this sounds about right. And so we're just going to do this. In the next example, we're going to assume air contains 23.1% oxygen by mass. I said it contains 20% oxygen, but 20% oxygen is for mole or volume or pressure. So we assume air contains 23.1% oxygen by mass. How many pounds of air is required or are required to combust 1 pound of methane? How many pounds of air do we need? All right, so again, this is just stoichiometry. First, in any stoichiometry problem, we need the balanced chemical equation. It's a standard combustion reaction, CO2 gas plus 2 water. Water is a liquid. And so this is what we're going to do. We're going to go from pounds of air to what? I mean pounds of CO2. 1 pound of CO2 to grams of CO2. From grams of CO2, we're going to go to moles of CO2. This is a gram to mole conversion. And then moles of CO2 to moles of O2. But O2 is pure, right? And so from moles of O2, then we'll go to grams of O2. And then pounds of O2. But this is pounds of O2, pure O2. And so from pounds of pure O2, we're going to go to pounds of air. So this is what they would call an advanced problem. An advanced problem because we have to do an additional step here to figure it out. So this is just pounds of air. Okay, so let's set this up here. So again, I'm going to start off with 1 pound of methane. And then I'll convert it into grams, 453.6 grams per pound. The pounds cancel, leaving me with grams of methane. And then I'll do a gram to mole conversion using the molar mass. I have to flip over the molar mass. 16.05 grams per mole. That's for methane only. And so the grams of methane cancel, that leaves me with moles of methane. And then I could do a mole to mole conversion, and that is I need 2 moles of O2 molecules for every 1 mole of methane molecules. And so the moles of methane molecules cancel, at least with moles of O2 molecules. And then I need to do a mole to gram conversion using the molar mass. And so it's 32.00 grams of O2 for every mole of O2. The moles of O2 cancel. And then from grams of O2, we're going to go to, we're going pounds. We're going to pounds. So 1 pound is 453.6 grams. So the grams cancel. These are the pounds of O2. That's pounds of pure oxygen. I don't want pounds of pure oxygen. I want pounds of air. So tell me what the next conversion factor is. Tell me what the next conversion factor will be here that I'm going to tack on. The next, actually the final conversion factor.
That's pounds of O2 at the top, right?
Yep. So we have pounds of O2 at
So
the
it's
top.
like pound point something.
So we have
up
other
there.
elements in this, like nitrogen.
So tell me what it is. Hmm?
Why do you have, doesn't the grams over pound and panda per grams, don't they just cancel each other out?
Grams can't, yeah, grams cancel each other out.
So it's pounds.
So I have pounds of O2. I have pounds of O2 left.
Why do we need the grams per pound if we cancel it out with pound per gram?
And then percentage, right, the next conversion was a question.
Is here very percentage of error?
Yeah.
Oxygen needs to
Oh,
Cancel out.
yeah, okay, cancel these out.
Oh,
So
yeah.
like, do we need to put them? Why do we have them?
We have to put them, otherwise it doesn't convert. It doesn't convert. We gotta make sure the dimensions are all there. You have to show the cancellation. You can't just skip that step, because if you skip that step, the units don't work.
I just don't understand how we have it in reverse, because if you cancel those, it just equals one. Like, I don't understand why we have it twice.
Because it's gonna go from H4, and then it goes from.
Let me ask you this, is this 16.05 pounds per mole?
No, right.
That's why. It doesn't, what you say works mathematically, but it doesn't work logically. What you're saying is you're missing. If this were like a logical progression, you're missing a key step. And so even though it seems redundant, it's to keep the mathematical, what they call the logic going.
Okay.
Yeah. A lot of people skip it and make accidental mistakes, and I end up deducting a lot because they're missing. So you know, unless I'm asking just for the final answer, like multiple choice, go ahead, skip it, multiple choice. But if it's a free response, you better write some stuff in there, unless you know, because I check how you solve it. I'm waiting for the last conversion. How many times have we done percentage already? Percentage should be like the kindergarten stuff, because we started the semester off talking about percentages. So tell me what the next conversion factor is. Percentages, how many times have we done it? So many times.
Do you have to also include CO2?
No, we're done with CO2.
Okay, so times 100.
Because we need to go from air to oxygen,
Yeah.
so don't we multiply?
So you said, yeah, so you said times 100 what? 100 times 100?
No.
Lucian?
No.
No?
Sorry.
Well, did you already figure this out mentally?
It's 2.3 minus 100.
This one you should be able to do right away. 23.1% is what?
Oh, so 100 minus 20.
Well, just tell me what it is. 23.1% oxygen by mass means,
23.1 grams
23.1 grams.
okay,
out of 100
Yeah.
23.1 grams out of 100 what?
grams.
Grams of air.
That doesn't make sense. There's something missing.
Grams of oxygen out of 100 grams of air.
Yeah. But this is mass. Does it matter if we use grams or pounds?
Does not matter.
Or 23.1 pounds of oxygen for every 100 pounds of air. And so right off, that's good. You see that. You just gotta see that and then place it where it belongs. How do we place it where it belongs?
So
So what? How do we write it over here?
denominator is 100 pounds. Oh wait.
So the next one would be 20, denominator 23.1,
Yes.
and denominator is 100.
Yeah. It's going to be 23.1 pounds of oxygen, because we need to get rid of pounds of oxygen and replace it with
100 pounds of air.
air. Okay, now we're done. This is the logic of the dimensional analysis. We have to make sure everything cancels out properly in dimensional analysis. And we can see. I'm gonna stop this calculation right here though, so we can see how many pounds of pure oxygen we need. And so, it's gonna just be 1 divided by 1605 times 2. So I'm just gonna do 2 divided by 16.05 times 32. And so we need 3.987 pounds. Okay, up to here, we require 9.875 pounds of pure oxygen. So we need about 4 pounds of pure oxygen for every pound of methane. But since we're not using pure oxygen, we're using air, we're gonna need more than that. So this is gonna be times 100 divided by 23.1, which gives us 17.262 pounds of air required. $17.2. Okay, and then, so that's kind of an advanced problem. The advanced problem we see, we're gonna use, what do we call that?
Dimensional analysis.
Yeah. Let's see. Let me just do one more problem. The last problem we'll do is this.
Industrial look.
Let's say an alloy contains copper and aluminum, right? Let's say this is going to be 10 grams, 0 gram. How much aluminum in the alloy? It requires 107 milliliters of, let's go with 20.1% HCl by mass to react. And so this question is going to be 2 levels harder. And so one, we have the percentage, but we have 2 percentages in this. One, we have the percentage for the HCl, and the other, we're going to have a percentage for the alloy, although I'm not asking you for the percent. I'm just asking you how much aluminum is in this alloy. The percentage would be asked in a normal question. In a normal question, you might be asked, what is the percentage composition of this alloy in terms of aluminum? And so that's one additional step. So I'm skipping that last step here, but we're out of time, so we'll continue this next time.